let us journey together into the cold, silent depths of the outer solar system, far beyond the rocky inner worlds and the sprawling asteroid belt. Our destination is the realm of giants, the court of the colossal planet Jupiter, a world so immense it could swallow every other planet whole. Here, circling this behemoth, is a retinue of moons, each a world unto itself. We fly past the volcanic turmoil of Io and the ancient cratered face of Callisto to approach a sphere of brilliant white. From a distance, it appears as smooth as a polished stone, a placid globe of ice crisscrossed by the faintest of lines. This is Europa. It is a world wrapped in a shell of water ice, a frozen crust that gleams in the faint sunlight, reflecting it with an intensity that belies the frigid temperatures, which hover around minus 160 degrees Celsius, or minus 260 degrees Fahrenheit. As we embark on this journey together, we'd love to know where you are joining us from and what time it is in your part of the world. Please leave a comment and let us know. And if you enjoy stories about the cosmos and our quest to understand it, be sure to subscribe so you'll be notified when we release new explorations into the unknown. For beneath Europa's serene, frozen facade lies what may be the most exciting secret in our solar system: a vast, dark, liquid water ocean, a silent, global sea that could contain more than twice the amount of water found in all of Earth's oceans combined. This hidden ocean, warmed not by the distant sun, but by the constant gravitational push and pull from mighty Jupiter, makes Europa one of the most compelling targets in our search for life beyond Earth. It is a place that challenges our understanding of where life can exist, forcing us to look beyond sunlit surfaces to the dark, energy-rich interiors of distant worlds. But to understand this world's promise, we must first travel back in time, to a moment when it was nothing more than a faint speck of light in a primitive telescope, its true nature hidden for centuries. That faint speck of light found its first chronicler in the winter of 1610, in the city of Padua, part of the vibrant and intellectually fervent Republic of Venice. Here, a man named Galileo Galilei, a professor of mathematics already famous for his work on motion and mechanics, turned his attention to the heavens. He had not invented the telescope, an honor that likely belongs to a Dutch spectacle maker named Hans Lippershey. But he had done something arguably more important. Upon hearing vague reports of a device that made distant objects appear closer, Galileo, with his profound understanding of optics and his exceptional skill as a craftsman, set about constructing his own. His first versions magnified objects by a mere 3 times their normal size. But through painstaking work, grinding and polishing his own lenses, he soon produced an instrument capable of a 20, and eventually a 30 power magnification, a power that no one else in the world possessed. He first used it for more terrestrial and profitable purposes, demonstrating its military and commercial value to the Venetian Senate by showing them how it could spot ships at sea a full 2 hours before they could be seen with the naked eye. But Galileo's true passion lay beyond the horizon, in the celestial sphere that for millennia had been governed by the philosophical deductions of Aristotle and the complex mathematical model of Ptolemy, both of whom placed the earth at the center of all creation. In the early days of January, he aimed his new instrument at Jupiter, the brightest wandering star in the night sky. On the evening of January 7th, he noted what he at first took to be 3 small, faint stars, almost invisible to the naked eye, all positioned in a neat, straight line near the planet. It was a curiosity, but he assumed them to be part of the fixed, unchanging background of stars. The cosmos, according to the wisdom of the age, was perfect and immutable. Yet something about this observation must have intrigued him, because the very next night he looked again. What he saw was impossible. The 3 stars had moved. They were no longer in the same positions relative to Jupiter. A fixed star, by its very definition, could not move in such a way. A profound and dangerous idea began to form in his mind. Over the next week, despite the cold, he returned to his telescope with obsessive dedication, meticulously recording and sketching the positions of these strange lights night after night. He saw that they were not just moving, but they were oscillating back and forth, sometimes disappearing behind Jupiter, sometimes reappearing on the other side. He also discovered a 4th such light that had been initially hidden from his view. By January 15th, he had solved the puzzle. These were not stars. They were celestial bodies in orbit, not around the Earth, but around Jupiter. He had discovered moons, the first to be seen by human eyes since our ancestors first gazed upon our own. This was more than just a discovery. It was a revolution contained within a few pages of notes. The idea that the Earth was the center of all motion, the cornerstone of both scientific and religious doctrine for over 1,500 years, had been shattered. Here was plain, irrefutable proof of a secondary center of motion in the heavens. These 4 new worlds, which he called the Medicean stars, in a shrewd and successful attempt to win the patronage of the powerful Cosimo II de' Medici, Grand Duke of Tuscany, demonstrated that the universe was not as simple or as earth-centered as everyone had believed. He designated them with Roman numerals: Jupiter 1, Jupiter 2, Jupiter 3, and Jupiter 4, in order of their proximity to the planet. The world we now call Europa was, for a very long time, simply known as Jupiter 2. But the history of discovery is rarely a straight line, and Galileo was not entirely alone in his observations. In the Margraviate of Ansbach, in what is now Germany, Another astronomer named Simon Marius, also using a telescope of his own design, had been watching Jupiter. He would later claim to have observed the moons as early as late 1609, a few weeks before Galileo, but he did not publish his findings until his book, Mundus Jovialis, was released in 1614. This delay cost him the honor of being named their sole discoverer and ignited a bitter priority dispute, with Galileo angrily accusing Marius of plagiarism and fraud. While history has largely sided with Galileo for his prompt and systematic publication, it is now widely believed that Marius's discovery was independent, a case of two brilliant minds in different parts of Europe reaching the same incredible conclusion at almost the same historical moment. Yet Marius was to have his own lasting impact on our story. Lacking a powerful political family to flatter, he took a different approach to naming these new worlds. At the suggestion of the great astronomer Johannes Kepler, a man who was then in the process of discovering the laws of planetary motion, Marius proposed a more poetic and enduring set of names drawn from classical mythology. Since the planet was named for Jupiter, the king of the Roman gods, Kepler suggested naming the moons after his lovers. And so, the four worlds were given the names of figures from Greek legend who had been pursued by Zeus, the Greek equivalent of Jupiter, Io, a priestess of Hera, Ganymede, a beautiful Trojan youth, Callisto, a nymph sworn to Artemis, and Europa. The name Europa belonged to a Phoenician princess, the daughter of King Agenor of Tyre. As the ancient story goes, she was a woman of breathtaking beauty. And one day, while she was gathering flowers with her companions on the sun-drenched coast of the Mediterranean Sea, she caught the eye of Zeus himself. The god, inflamed with desire, transformed himself into a magnificent creature, a great bull of the purest white, with horns that shimmered like polished jewels. The bull was not fearsome, but gentle, and it approached Europa and her friends, who marveled at its placid nature. Emboldened, Europa adorned its horns with garlands of flowers, and growing ever more confident, climbed upon its broad back. This was the moment Zeus had been waiting for. The bull immediately charged, not into the fields of Phoenicia, but into the waves of the sea, carrying the terrified princess away from her home. It swam with powerful strokes across the vast expanse of water, all the way to the distant island of Crete. There, Zeus revealed his true form, and she became his consort, bearing him 3 sons who would become kings and judges in the underworld. The continent of Europe would eventually bear her name, a testament to her mythical journey from the East. For centuries, this lyrical naming system struggled to gain acceptance. Most professional astronomers preferred Galileo's more scientific, if less imaginative, numbering system. It was not until the mid-19th century that the mythological names finally became the standard, securing the legacy of both Marius and Kepler. The name Europa, born from a tale of a god disguised and a princess carried across a great sea to a new and unknown land, had finally found a permanent home. It now belonged to a real world, a sphere of ice and rock orbiting a gas giant hundreds of millions of kilometers or hundreds of millions of miles from the shores of Crete. That ancient story of a journey across a vast and mysterious body of water would prove to be more prophetic than either Kepler or Marius could have ever imagined. The true nature of this distant, ice-white world remained a complete mystery, a blank canvas upon which only myths could be written, until the dawn of a new age of exploration, when humanity began to send its own emissaries out into the great ocean of space. For more than 3.5 centuries after Galileo first saw it, Europa remained little more than a point of light, its secrets held fast across the vast gulf of space. Telescopes on Earth grew larger and more powerful, allowing astronomers to measure its size, calculate its orbit with exquisite precision, and even analyze the sunlight reflecting from its surface. These observations provided the first tangible clues about its nature, revealing that its surface was overwhelmingly composed of water ice. They also measured its density, which was far too high to be a ball of pure ice. It had to have a substantial, rocky core. But these were broad strokes, a sketch of a world with no fine detail. The true beginning of our understanding, the moment Europa began to transform from an astronomical object into a geological place, had to wait for the arrival of those first emissaries. This new age of exploration began in the early 1970s with two audacious robotic pioneers, appropriately named Pioneer 10 and Pioneer 11. They were humanity's first messengers to the outer solar system, built to be hardy and resilient. Their primary mission to brave the then feared asteroid belt and to make the first ever close-up reconnaissance of the gas giant Jupiter. The moons were secondary targets, almost an afterthought. Pioneer 10 flew past Jupiter in December of 1973, followed by Pioneer 11 a year later. Their cameras were simple by later standards, providing only grainy, distant images of Europa that were barely an improvement over the best telescopes on Earth. But their instruments did something no terrestrial observatory could. As they hurtled through the Jovian system, they were bombarded by a ferocious storm of radiation, energetic particles trapped and accelerated by Jupiter's immense magnetic field, a field so powerful it dwarfs our own planets. They measured this environment, confirming it was one of the most hazardous in the solar system, a fact that would profoundly shape all future missions. And they made more precise measurements of Europa's mass and size, confirming it was a world of rock, wrapped in a thick, global layer of what appeared to be water. Yet, it was still a world without a face, a featureless, white orb. The real revelation came at the end of that decade, with the launch of two of the most successful exploratory craft ever built, Voyager 1 and Voyager 2. Launched in 1977, they were designed to take advantage of a rare celestial alignment, a grand confluence of the outer planets that occurs only once every 175 years, allowing them to perform a grand tour, using the gravity of each giant planet to slingshot them onto the next. They were equipped with far more sophisticated cameras and a suite of advanced scientific instruments. Their journey was to be our first true voyage through the archipelago of worlds that orbited Jupiter. In March of 1979, Voyager 1 swept through the system. Its trajectory was optimized for a close look at the volcanic moon Io and the giant moon Titan at Saturn, so its encounter with Europa was a relatively distant one, passing at a range of about 734,000 kilometers, or nearly 456,000 miles. But even from this immense distance, the images it sent back across the empty space were stunning. They revealed a world unlike any other, where scientists had expected to see a surface pockmarked with craters, the ancient scars of cosmic impacts that litter almost every other solid body in the solar system, from our own moon to Mercury. They saw an eerie, almost perfect smoothness. Europa was a celestial billiard ball, shockingly bright and shockingly unblemished. This single observation was revolutionary. A lack of craters implies a young surface, one that is being actively and continuously renewed from within, erasing the evidence of its long history of bombardment. Something was constantly paving and over the old terrain, wiping the slate clean. And crisscrossing this impossibly smooth surface was a complex network of long, dark lines. They stretched for hundreds, sometimes thousands of kilometers or thousands of miles, intersecting and overlapping in a dense, planet-encircling web. In the low-resolution images from Voyager 1, they looked as though a celestial artist had taken a fine-tipped pen and drawn delicate, intricate patterns across a smooth, white sphere. The mystery deepened only 4 months later. In July of 1979, Voyager 2 flew much closer, passing within just over 200,000 kilometers, or about 125,000 miles, of Europa's surface. Now, with a resolution many times greater, the world came into focus. The smooth plains were confirmed, but the lines were revealed to be not simple cracks, but complex geological features. They were vast, shallow, double-ridged grooves, like immense, frozen versions of freeway interchanges and railway tracks, some stretching from horizon to horizon. And they were not gray or black, as they had first appeared, but a distinct reddish-brown, a deep, rusty hue that stood in stark contrast to the brilliant white of the surrounding icy plains. Suddenly, scientists were faced with a cascade of baffling questions. What was this strange, dark, reddish material? And where did it come from? What immense geological forces could fracture a moon's entire surface in such a specific, linear fashion? And most importantly, what was the mechanism that was constantly resurfacing the entire moon, keeping it so pristine and young? The images from Voyager 2 also showed another type of terrain, regions where the smooth, ordered plains and long lines seemed to have been shattered into enormous icy rafts, which had then drifted apart, rotated, and frozen back into place, like icebergs in a thawing Arctic sea. This jumbled, disrupted landscape was dubbed chaos terrain, and it looked for all the world like a place where the solid crust had been broken and disturbed by a liquid or slushy layer beneath. As scientists at NASA's Jet Propulsion Laboratory and universities around the world pored over these startling new images, a breathtaking hypothesis began to take shape, connecting all these disparate, mysterious clues. The smoothness of the surface, the planet-spanning cracks, the chaos terrains, they could all be explained if Europa's frozen crust was not solid all the way through. What if it was merely a shell, perhaps a few tens of kilometers or a few tens of miles, thick, floating on top of a vast, hidden ocean of liquid water? The engine for this hidden world could be Jupiter itself. As Europa follows its slightly elliptical path, the giant planet's immense gravity constantly tugs on it. But the pull is stronger on the near side and weaker on the far side. This differential pull, combined with the gravitational influence of the other large moons, Io and Ganymede, means that Europa is continuously stretched and squeezed, its entire body flexing and deforming with every orbit. This constant internal friction, a process known as tidal heating, could generate enough warmth to maintain a liquid ocean beneath the ice, far from the life-giving warmth of the sun. The long, reddish cracks could be places where the icy shell has fractured under this relentless tidal stress, allowing water from the ocean below, perhaps laced with salts and other minerals from the rocky seafloor, to well up and freeze onto the surface. The chaos terrains could be areas where the shell has temporarily melted or collapsed into the ocean below. The Voyager flybys were fleeting, a few precious hours of observation before the probes sped onward to Saturn and beyond, becoming humanity's first emissaries to interstellar space. They had given us a glimpse of a world more dynamic and mysterious than anyone had dared to imagine. They had replaced the old mystery of a blank, white orb with a new and far more profound one, the mystery of a hidden ocean. But a hypothesis, no matter how compelling, is not proof. To find that, we would need to go back, not for a passing glance, but for a long, lingering look. We would need a dedicated mission, a probe that could orbit Jupiter for years, studying Europa again and again, armed with instruments designed to peer beneath the ice. The age of reconnaissance was over. The age of dedicated investigation was about to begin. That dedicated investigation would be entrusted to a spacecraft named, fittingly, Galileo, a robotic explorer designed to become the first artificial satellite of Jupiter, destined to spend years in patient orbit rather than mere hours in a fleeting flyby. Its conception was ambitious, a sophisticated two-part vessel consisting of a large orbiter, intended to circle the giant planet for years, and a smaller atmospheric probe, designed to make a one-way, suicidal plunge into Jupiter's swirling cloud tops. Yet the path to discovery is seldom smooth. The mission was originally scheduled for a 1986 launch aboard the Space Shuttle Atlantis, which would have carried a powerful Centaur upper stage to propel Galileo on a direct 2.5-year path to Jupiter. But in January of that year, the tragic loss of the Space Shuttle Challenger and its crew grounded the entire fleet and led to a complete overhaul of safety protocols. The powerful liquid-fueled Centaur was deemed too hazardous to carry in the shuttle's payload bay, forcing mission planners to switch to a less powerful solid-fuel rocket. This new rocket was not strong enough to send the massive 2.5-ton spacecraft on a direct course. The engineers and navigators at NASA's Jet Propulsion Laboratory were forced to devise a new, far more circuitous route, a masterpiece of orbital mechanics that would require Galileo to journey for more than 6 years. Launched in October of 1989, it first fell inward, toward the Sun, to fly past Venus, stealing a sliver of the planet's orbital energy. This catapulted it back toward our own world for 2 successive flybys of Earth, each one adding more speed, like a slingshot being pulled back twice. This winding, gravity-assisted journey of nearly 3.9 billion kilometers, or 2.4 billion miles, was a triumph of ingenuity. But the long years in space took their toll. The mission's greatest trial came in April of 1991, as the spacecraft coasted between Earth and the asteroid belt. The command was sent to unfurl its main communications dish, a magnificent 18-foot or 5.5-meter wide high-gain antenna that looked like a delicate gold mesh umbrella. It was the key to sending back the torrent of data and high-resolution images the mission was designed to gather. But it refused to open fully. 3 of its 18 ribs, likely stuck fast by lubricants that had been degraded by the long years in storage and the vibrations of launch, remained stubbornly locked in place. For months, engineers on Earth tried everything they could think of to free it, warming and cooling the mechanism, spinning the spacecraft at high speeds, even hammering the stuck components by rapidly firing the craft's thrusters. Nothing worked. The great antenna was useless. It was a potentially crippling blow, a disaster that threatened to reduce the billion-dollar mission to a near-total failure. The hopes of a generation of planetary scientists now rested on a tiny, secondary, low-gain antenna, a simple dish no bigger than a dinner plate, designed only for emergencies. Its data transmission rate was agonizingly slow, thousands of times weaker than the main antenna. But rather than admitting defeat, the mission's engineers performed one of the most remarkable rescue operations in the history of space exploration. They rewrote the spacecraft's operating software from hundreds of millions of miles away, teaching it powerful new data compression algorithms to make the most of every precious bit. They devised new ways to record data on the onboard tape recorder and transmit it slowly, patiently, back to the giant radio telescopes of the deep space network on Earth. The mission was saved, not by brute force, but by sheer intellectual brilliance. Finally, on December 7th, 1995, after its long and perilous journey, Galileo arrived. As it screamed toward the planet at a speed of 170,000 kilometers per hour, or 106,000 miles per hour, it flawlessly executed its two primary tasks. It released its atmospheric probe, which plunged into Jupiter's clouds, sending back the first and only direct measurements of a gas giant's atmosphere before being crushed and vaporized by the immense pressure. A few hours later, the main orbiter fired its primary engine for a crucial 49-minute burn, slowing itself just enough to be captured by Jupiter's immense gravity. The age of dedicated investigation had officially begun. For the next 8 years, Galileo looped through the Jovian system, a lonely, robotic moon in its own right. Its primary mission was to study Jupiter, but its orbital tour was designed to include dozens of close encounters with the large moons. And with each pass of Europa, the evidence for a subsurface ocean grew more and more compelling. The high-resolution images were breathtaking, revealing the chaos terrains in stunning detail. In a region later named Connemara Chaos, the cameras showed vast tabular plates of ice that had been clearly broken apart, tilted, and rotated before freezing back into place, like immense icebergs on a terrestrial sea. The reddish lineae were seen to be complex systems of parallel ridges and central grooves, suggesting the crust had been repeatedly pulled apart and filled in by new material from below. But the definitive breakthrough evidence did not come from a camera. It came from an instrument called a magnetometer, designed to measure the strength and direction of magnetic fields. At the helm of this investigation was the brilliant planetary scientist Margaret Keivelson. Jupiter, being a gigantic, rapidly spinning ball of metallic hydrogen, generates the most powerful magnetic field of any planet in our solar system. This magnetic field is not static. As the planet spins once every 10 hours, the field whips around with it, washing over the orbiting moons like a colossal, invisible wave. Keivelson and her team knew that if Europa were a simple, inert ball of ice and rock, Jupiter's magnetic field would pass through it relatively undisturbed. But that is not what their instrument saw. As Galileo flew through the space around Europa, the magnetometer detected a second, distinct magnetic field, one that was embedded within the moon itself. This was not a permanent field, like the one generated by Earth's molten iron core. Instead, it was an induced magnetic field. This is a phenomenon that occurs when a conductive material is exposed to a changing magnetic field. Just as moving a magnet near a coil of wire will generate, or induce, an electrical current in that wire, Jupiter's rotating magnetic field was inducing electrical currents somewhere inside Europa. And these powerful currents, in turn, were generating their own magnetic field. The signature was unmistakable. Europa's induced field was a perfect response to Jupiter's primary field. It flipped its own polarity in perfect time with Jupiter's rotation. Kaivalson and her team considered every possibility. The field could not be generated in a solid ice shell, as ice is a very poor electrical conductor. It could not be coming from a molten core, as the signature was wrong, and a moon of Europa's size would have cooled and solidified long ago. The only explanation that fit the data perfectly was the presence of a global layer of a highly conductive material near the surface. The most plausible conductor, by far, was a liquid water ocean laced with dissolved salts and minerals, much like the oceans of Earth. The saltier the water, the better it conducts electricity, and the strength of the induced field suggested an ocean with a salinity comparable to our own. This was it. This was the moment, the hypothesis, born from the fleeting images of Voyager, became a robust scientific theory, supported by hard, quantitative data. The ghostly readings from a magnetometer, translated through the language of physics, had provided the strongest evidence yet that beneath Europa's frigid, shattered crust lay a dark, vast, and salty sea. The Galileo mission had peered beneath the ice without ever touching it, transforming our perception of this small, distant moon forever, and elevating it to the very highest tier of worlds to be searched for life. While the invisible language of magnetic fields provided the most definitive proof of Europa's hidden sea, it was Galileo's cameras that gave that ocean a voice, writing its story across the face of the ice in a dramatic and bewildering script. The spacecraft's solid-state imager, a far more advanced successor to the cameras of the Voyager probes, captured the Europan surface with a clarity that was, at times, sharp enough to see features the size of a city bus. As these images, painstakingly transmitted bit by bit across the solar system, were assembled on Earth, they confirmed that Europa's face was a geological wonderland, a landscape shaped not by the external violence of impacts, but by the restless, internal energy of a world in constant motion. The most dominant features, the ones that defined the moon's global appearance, were those long, reddish-brown lines, the lineae. From Voyager's distant perspective, they had appeared as simple pen strokes, Galileo revealed them to be far more complex and imposing. The majority were not cracks, but vast, parallel ridges, sometimes running side by side for over 1,000 kilometers, or more than 600 miles. These double ridges, as they came to be called, looked like monumental earthworks, as if a race of giants had built a network of highways across the entire moon. Some were truly colossal, rising up to 300 meters, or nearly 1,000 feet, from the surrounding plains, and stretching 20 to 40 kilometers, or 12 to 25 miles, in width. And they were everywhere, cutting across older ridges, being cut by younger ones, creating a global stratigraphic puzzle that geologists are still working to unravel. The prevailing theory for their creation paints a picture of incredible tidal stress. As Jupiter's gravity stretches and compresses Europa, the rigid, brittle ice shell at the very surface cracks. Water, or warm, slushy ice from deeper within the shell, or perhaps from the ocean itself, is then squeezed up into these fractures. As this material erupts onto the frigid surface, where the temperature is low enough to freeze nitrogen solid, it instantly freezes, expanding as it does so. This expansion pushes the edges of the crack upwards and outwards, building up the twin ridges over repeated cycles of cracking and healing. Each set of ridges is a scar from a wound that has healed itself, a testament to the moon's ongoing struggle against the tidal forces that seek to tear it apart. The mysterious reddish-brown material, which seems to coat these ridges and stain the surrounding terrain, is likely the chemical signature of the world below. Scientists believe it is a mixture of salts and sulfur compounds dredged up from the ocean. On the surface, this material is subjected to the relentless bombardment of high-energy particles trapped in Jupiter's magnetosphere, a process that alters its color and chemical state. These lines, therefore, are not just geological features. They are potential chemical windows, offering us a discolored, irradiated glimpse into the composition of the hidden sea. While the lineae spoke of a process of cracking and healing, other regions of the surface told a far more violent and chaotic story. These were the aptly named chaos terrains, places where the ordered, linear landscape of the icy plains had been utterly destroyed. Here, the surface had been shattered into a flotilla of immense, angular blocks of ice. The Galileo images of regions like Connemara Chaos, an area roughly the size of the state of New Jersey, were stunning. They showed these huge ice rafts, some more than 10 kilometers or 6 miles across, which had clearly been jostled, tilted, and rotated, like pieces of a jigsaw puzzle thrown into disarray. What was remarkable was that the original patterns of ridges and cracks were often still visible on the surfaces of these individual blocks, allowing scientists to digitally cut them out and, like cosmic archaeologists, piece them back together, proving beyond doubt that they had once formed a coherent crust that had later been catastrophically disrupted. The formation of these chaotic landscapes is thought to be one of the most direct expressions of the ocean's influence on the surface. The leading model suggests that a massive plume of warm, buoyant ice, or perhaps even a huge blob of liquid water from the ocean itself, slowly rises through the colder, denser ice shell. As this body of heat and fluid nears the surface, it causes the overlying ice to melt, thin, and ultimately collapse. The solid crust breaks apart, and the resulting blocks are left to drift and refreeze in a jumbled, disorganized matrix of new ice, slush, and upwelled ocean brine. These are places where the boundary between the ocean and the surface has temporarily failed, where a large-scale heat exchange has taken place, turning a stable, rigid plane into a turbulent, shifting ice jam on a planetary scale. If the lineae are scars, the chaos terrains are open wounds, places of profound upheaval that expose the dynamic and sometimes violent nature of the ice-ocean interface. And scattered across the vast, smooth plains, between the great ridges and the chaotic jumbles, Galileo's cameras found a third, more subtle, but equally important type of feature. Small spots, typically about 10 kilometers or 6 miles in diameter, which scientists nicknamed lenticulae, from the Latin for freckles. These freckles dot Europa's face in their thousands and come in several forms. Some are domes, where the surface has been gently pushed upward. Others are pits, where the ground has sunk into a shallow depression. And some are simply spots of dark, smooth ice that have replaced the bright, white plains. Their existence points to a process happening entirely within the ice shell itself, a phenomenon known as solid-state convection, or diaporism. The ice shell is not a uniform, static block of ice. It is heated from below by the ocean and cooled from above by the vacuum of space. This temperature difference means the ice at the bottom of the shell is warmer, and therefore slightly less dense and more buoyant than the colder, more brittle ice at the top. Over immense geological timescales, blobs of this warmer ice can slowly begin to rise, pushing their way upward through the colder, stiffer ice above them, much like the blobs of wax rising in a lava lamp. When one of these icy diapers reaches the upper crust, it pushes the brittle surface ice upward, creating a dome. In other cases, denser material from the surface might sink downwards, creating pits. These freckles are the surface expression of a slow, churning motion within the ice shell itself, proof that Europa's entire frozen crust is in a constant, convective state of circulation. Together, the lineae, the chaos terrains, and the lenticulae paint a cohesive and breathtaking picture of a geologically active world. They show us a world with a brittle, fracturing surface giving way to a warm, convecting interior, all of which rests upon a globe-spanning, liquid water ocean. The face of Europa is a map of its inner life, a direct link between the chemistry of the hidden sea and the harsh, radioactive environment of space. It is a record of a world constantly renewing itself from within, a dynamic interface where the ingredients for life, brought up from the dark ocean below, are mixed and processed by the forces of the Jupiter system. This dynamic and violent portrait, written in the language of geology across Europa's face, offered a powerful, albeit indirect, connection to the ocean below. It showed a world where the boundary between the inner liquid realm and the outer frozen surface was a zone of constant exchange, a place of fracturing, melting, and slow, churning convection. But what if this connection was not always so subtle? What if, in certain places, the ocean could breach the icy dam entirely, not just seeping up to fill cracks, but erupting with force, venting its contents directly into the blackness of space? This was a tantalizing possibility, one that would transform our view of Europa from a sealed treasure chest to one that was actively offering up its secrets. The evidence for such a dramatic phenomenon would not come from a dedicated Jovian explorer like Galileo, but from a sentinel in a very different location, an observatory circling our own home planet. This was the Hubble Space Telescope, a marvel of engineering launched in 1990, which, from its perch high above the distorting haze of Earth's atmosphere, could observe the cosmos with unprecedented sharpness, particularly in the wavelengths of ultraviolet light that are invisible to the human eye. In 2012, a team of scientists led by Lorenz Roth of the Southwest Research Institute was using Hubble not to take a direct picture of Europa, but to study its exceedingly thin atmosphere, a tenuous envelope of gas 100 billion times less dense than our own. They were particularly interested in Europa's aurora, the faint glows of light created when the energetic, charged particles of Jupiter's magnetosphere slam into this atmosphere. By using Hubble's powerful spectrograph to break the auroral light down into its constituent colors, or wavelengths, they could identify the chemical composition of the gas being struck. As expected, they found the signature of oxygen, which is constantly being created as the radiation bombards the surface ice. But over Europa's south polar region, they saw something astonishing. They detected localized, intense spikes in the emissions of both atomic hydrogen and atomic oxygen, in precisely the 2-to-1 ratio that constitutes water. It was the chemical fingerprint of vast quantities of water molecules being ripped apart by a torrent of electrons. The most logical explanation was that they were witnessing the aftermath of a colossal plume of water vapor rising from the surface and being blasted by the surrounding plasma. The evidence was compelling but indirect, and the phenomenon was fleeting. On subsequent observations, the signal was gone. The potential geyser was either intermittent, or they had simply been lucky to be looking at the right time. the hunt was on. 2 years later, a different team, this one led by William Sparks of the Space Telescope Science Institute, decided to try a different, more direct approach. Their idea was elegant. Instead of looking for the light emitted by the plume's destruction, they would look for the plume's shadow. They waited for moments when Europa, in its steady orbit, would pass in front of Jupiter from Hubble's perspective. Against the bright, relatively uniform, and complexly patterned backdrop of Jupiter's clouds, a plume of water vapor erupting from Europa's edge would absorb some of the ultraviolet light coming from the planet behind it. If they could catch it in the act, the plume should appear as a dark, finger-like silhouette extending from the moon's limb. For months, they watched these transits, and in 2014, they found exactly what they were looking for. Extending from Europa's southern hemisphere was a dark patch that looked for all the world like a plume of material rising some 200 kilometers, or 125 miles, into space before arcing back down toward the surface. They found similar candidate plumes on subsequent transits in 2016, some in the very same location where Lorenz Roth's team had seen the auroral hotspots. This was a different line of evidence, using a different technique, but it pointed to the same incredible conclusion. Europa was an active world, one that was periodically spewing its water into space. The excitement in the planetary science community was immense, but it was tempered with caution. The signals from Hubble were at the very limit of the telescope's capabilities, difficult to extract from the noisy data. Some remained skeptical, wondering if the observations could be instrumental artifacts or misinterpretations. What was needed was a third, independent line of evidence, a final piece to lock the puzzle into place. That piece would come not from a new mission, but from a ghost of a mission past. Xianjie Jia, a space physicist at the University of Michigan, was haunted by an old mystery from the Galileo mission. On a close flyby in December of 1997, the spacecraft had passed just 400 kilometers, or 250 miles, over a region of the southern hemisphere. During this pass, its magnetometer had recorded a strange and sharp deflection in the local magnetic field, a bend that the original science team had noted but couldn't fully explain. At the same time, its plasma instrument had detected a sudden, dramatic spike in the density of charged particles. Intrigued by the new Hubble results, Jia and his team decided to go back into the 2-decade-old Galileo data and re-examine this anomaly with modern modeling techniques. They asked a simple question: what would a spacecraft's instruments detect if it flew directly through a water vapor plume? Their models predicted that as the water molecules erupted into space, they would be hit by the storm of radiation surrounding Europa and almost instantly have their electrons stripped away, a process called ionization. This would create a localized, dense cloud of new plasma. A cloud of plasma, being electrically charged, would interact powerfully with Jupiter's magnetic field, causing it to bend and drape around the plume. Furthermore, a plasma instrument flying through this cloud would register a sudden jump in density. The model's predictions were a perfect match for the strange, unexplained data from the 1997 flyby. The mysterious magnetic deflection and the sudden plasma spike were the precise signatures of a spacecraft flying through an active plume. Without even knowing it at the time, Galileo had almost certainly tasted the ocean's breath. This discovery, unearthed from old data, provided the powerful in situ confirmation that had been missing. The case for European plumes was now incredibly strong. The implications were nothing short of revolutionary for the future of exploration. The single greatest challenge to studying Europa's ocean had always been the monumental difficulty of getting to it, of having to design a lander that could somehow drill through an ice shell that might be anywhere from 3 to 30 kilometers, or 2 to 18 miles, thick. An engineering feat far beyond our current capabilities. But the plumes changed everything. They meant that Europa was, in effect, delivering samples of its ocean directly into space. A future mission would no longer need to drill. It would simply need to fly through one of these plumes with the right instruments, like a whale shark swimming through a cloud of plankton, to collect and analyze the ocean's contents. This realization opened a direct pathway to answering the most profound questions about this icy world. A spacecraft could use a mass spectrometer to measure the precise chemical makeup of the plume, searching for the complex organic molecules that are the building blocks of life. It could measure the salinity, the acidity, and the chemical disequilibrium of the water, all key factors in assessing its potential habitability. The dream of sampling a potentially life-bearing alien ocean had suddenly shifted from a distant, almost impossible goal to a tangible, achievable objective for the next generation of explorers. And what a sample it might prove to be, for it is the contents of that ocean, not just its existence, that elevates Europa into the highest echelons of astrobiological interest. The discovery of a vast, hidden sea was a monumental achievement, but it was only the first step. To assess whether this distant world could actually be a home for living things, a cradle for biology, we must ask a more fundamental set of questions. We must look for what we understand to be the 3 essential requirements for life as we know it, a trinity of ingredients that, when brought together, create a habitable environment. These are liquid water to act as a solvent, the essential chemical elements to serve as the building blocks of biology, and a source of usable energy to power the complex machinery of metabolism. The first ingredient, a medium where the chemistry of life can unfold, is present on Europa in breathtaking abundance. The data from Galileo's magnetometer, combined with our understanding of the moon's geology, paints a picture of a global ocean of salty, liquid water that has likely existed for billions of years, a stable environment beneath the protective shield of the ice. Its volume is staggering, estimated to contain more than twice the amount of water found in all of Earth's oceans, rivers, and lakes combined. If you were to gather all the water on our own blue planet into a single sphere, it would be dwarfed by the sphere of water hidden within Europa. It is an ocean of truly planetary scale, a dark, silent, and unimaginably vast potential habitat. But water alone is not enough. A sterile, empty ocean cannot support life. It needs the right raw materials, the chemical inventory from which to build cells. On Earth, the essential elements for life are often summarized by the acronym CHNOPS, representing the 6 most crucial elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The great question, then, was whether Europa's ocean was merely water, or if it was a rich, chemical soup. The evidence suggests it is the latter, with these essential ingredients being supplied to the ocean from 2 distinct directions, from above and from below. The delivery from below begins with the moon's very formation. Europa is not just a ball of ice. Its density tells us that beneath the water and ice lies a large, rocky mantle, much like the mantle of our own Earth. This rock would have formed from the same primordial cloud of gas and dust that created the sun and all the planets, a cloud that was rich in all the necessary elements. The same tidal heating that keeps the ocean liquid would also be working on this rocky core, kneading and flexing it, likely generating enough heat to drive geological activity on the seafloor. It is therefore highly probable that Europa's ocean floor is not a cold, dead, static place. Instead, it could be a dynamic volcanic landscape, home to hydrothermal vents. On Earth's ocean floors, these vents are astonishing oases of life. They are fissures in the planet's crust where superheated, mineral-rich water, having circulated through the hot rock below, gushes back out into the cold ocean. This water is a chemical cocktail laden with compounds of sulfur, iron, and other elements leached from the rock. Such vents on Europa's seafloor would serve as a constant source of chemical enrichment for the ocean, steadily supplying it with the raw materials necessary for life. At the same time, the ocean is likely being stocked from above. For 4.5 billion years, the surface of Europa has been bombarded by a steady rain of comets and asteroids. These cosmic wanderers are known to be rich in organic compounds, the complex carbon-based molecules that are the very foundation of life. This celestial delivery service would have coated Europa's icy shell with a thin veneer of these vital precursors. This material does not simply sit on the surface forever. The geological processes we see, the fracturing that creates the lineae, the cataclysmic collapse of chaos terrains, the slow, churning convection of the ice shell, are all mechanisms for surface-to-ocean transport. Over millions of years, this cosmic bounty of carbon and nitrogen is churned downwards, mixed into the ice, and ultimately delivered into the liquid water below. Europa's ocean, therefore, is not a pristine, isolated system. It is a world that is chemically fed by both its own rocky heart and by the cosmos itself. This leaves us with the third and most crucial ingredient: energy. Life cannot exist in a state of perfect equilibrium. It needs a flow of energy, a chemical imbalance to exploit in order to power its existence. In the blackness of Europa's ocean, hundreds of millions of miles from the sun, there can be no photosynthesis. Any life that exists there must survive on a different kind of energy. Once again, Europa appears to provide not one, but two potential solutions. The first and most dramatic source of energy lies on that dark seafloor. The same hydrothermal vents that supply the ocean with chemical building blocks would also create powerful energy gradients. The water emerging from these vents would be chemically very different from the surrounding ocean water, creating a state of disequilibrium. On Earth, entire ecosystems thrive in the total darkness around these vents through a process called chemosynthesis. Here, microbes, instead of using sunlight, harness the chemical energy released when compounds like hydrogen sulfide from the vents react with oxygen or other substances in the seawater. These microbes form the base of a food chain that can include tube worms, clams, and shrimp, all living in complete independence from the sun. The possibility of such self-contained, chemosynthetic ecosystems thriving on Europa's seafloor is one of the most exciting prospects in all of planetary science. The second source of energy is even more exotic: a complex chemical cycle driven by the fury of Jupiter itself. Europa's surface is not a peaceful place. It is constantly bathed in the intense radiation of Jupiter's magnetosphere. This radiation acts like a giant particle accelerator, smashing into the frozen surface and splitting water molecules apart in a process called radiolysis. This creates a host of highly reactive, energy-rich chemicals, most notably oxygen and hydrogen peroxide. These molecules are powerful oxidants, the very same types of chemicals that animals on Earth use to burn their food for energy. This surface chemistry, powered by radiation, is constantly creating one half of a chemical battery. The other half is being created on the seafloor by the hydrothermal vents, which release reducing agents like hydrogen sulfide. The geological churning of the ice shell completes the circuit. As the ice convects and chaos terrains form, the oxidants created on the surface are transported downwards into the ocean. Here, they can meet the reductants welling up from the seafloor. This mixing of substances from above and below would create a planet-wide chemical disequilibrium, a constant source of energy that life could potentially tap into. Europa, it seems, may possess all three ingredients for life in abundance. It has a vast and stable ocean. It has a rich supply of the necessary chemical elements delivered from its own core and from the heavens. And it has at least 2 plausible mechanisms for generating the chemical energy that living things require. It is a complete system, a habitable world defined not by the gentle warmth of a nearby star, but by the relentless gravitational power of a giant planet. The stage is set, the ingredients are present, and the potential for a biological story to have unfolded in that dark, hidden ocean is profoundly, tantalizingly real. To turn this tantalizing potential into tangible knowledge, to move from the realm of well-reasoned theory into the world of direct observation, humanity has begun to prepare a new wave of emissaries, robotic explorers far more advanced than any that have come before. The Galileo mission, for all its groundbreaking success, had only managed to open the book on Europa. It was now time to send missions designed to read the pages. The first of these, a flagship mission from the United States National Aeronautics and Space Administration, is an endeavor focused with laser-like precision on this one icy moon. It is called the Europa Clipper. The name is a nod to the swift 19th century sailing ships that plied the oceans of Earth, carrying precious cargo between continents. This new clipper is designed for a similar purpose, to repeatedly ply the ocean of space around Jupiter, returning a cargo of priceless data about the world that may hold an ocean of its own. Its design is a masterful solution to the single greatest danger of the Jovian system, the radiation. Jupiter's magnetic field traps a torus of charged particles, a donut-shaped storm of electrons and ions that whirl around the planet at near the speed of light. This environment is so lethal that a spacecraft in a simple, close orbit around Europa would be bombarded with so much radiation, its electronic brain would be fried in a matter of months. So, Clipper will not orbit Europa directly. Instead, it will enter a long, looping, elliptical orbit around Jupiter itself. The genius of this flight path is that it will spend most of its time far from the most intense radiation belts, in the relative safety of the outer Jovian system. But on each orbit, its trajectory will be precisely calculated to bring it screaming in for a close, low-altitude flyby of Europa. After each of these brief, data-rich encounters, it will swing back out into the safety of deep space to process its findings and transmit them back to Earth. Over the course of its mission, Clipper is planned to perform nearly 50 of these high-speed skate-bys, some coming as low as 25 kilometers or 16 miles above the icy surface. It will be a reconnaissance campaign on an unprecedented scale, painting a comprehensive, high-resolution picture of the entire moon. Launched in the month of October in the year 2024. The spacecraft is now on its long, looping journey, a multi-year voyage that will see it perform gravity-assist flybys of both Mars and Earth to build up the tremendous speed needed to reach the outer solar system. When it finally arrives in the early 2030s, it will bring to bear a suite of 9 sophisticated scientific instruments, each designed to answer a specific, crucial question about Europa's potential for life. To map the ocean it cannot see, Clipper carries an instrument that will act like a planetary-scale, ground-penetrating radar. It will send radio waves deep into the ice, listening for the distinct reflection that will signal the boundary between the solid shell and the liquid water below. These signals will, for the first time, reveal the thickness of the ice, mapping the global contours of the hidden ocean and searching for pockets of water that might be trapped within the shell itself. A far more sensitive magnetometer will follow up on Galileo's landmark discovery, measuring the induced magnetic field with much greater precision to confirm the ocean's existence and better determine its depth and, crucially, its salinity, a key factor in its habitability. A heat detector, a sensitive thermal imager, will scan the surface for hot spots, anomalous regions where the temperature is slightly higher than the surrounding terrain. Such a signature could betray the location of a recent plume eruption, or a place where the ice shell is particularly thin, where the ocean's warmth is closest to the surface. A suite of powerful cameras will map nearly the entire moon at resolutions hundreds of times better than Galileo, allowing geologists to study the lineae and chaos terrains in exquisite detail, and to look for any changes that may have occurred in the intervening decades, the first step in creating a planetary-scale geological movie. But perhaps the most exciting instruments are those designed to taste the moon itself. Spectrometers will analyze the light reflecting from the surface to create detailed chemical maps, identifying the composition of those mysterious reddish-brown salts and searching for organic molecules. And most critically, other instruments are designed specifically to fly through any plumes that might be erupting, capturing, and analyzing the gas and ice particles directly. They will act as a cosmic tongue and nose, capable of sniffing out the chemical makeup of the ejected ocean material, giving us our first direct analysis of that hidden alien sea. Europa Clipper is not alone on its journey. It is part of a collaborative international effort to unlock the secrets of the Jovian system. Preceding it by just over a year was the launch of a mission from the European Space Agency, an equally ambitious explorer called the Jupiter Icy Moons Explorer, or JUICE for short. Where Clipper's focus is singular, JUICE's is broader. Its mission is to perform a comparative study of 3 of the Galilean moons, Ganymede, Callisto, and Europa. Having launched in April of 2023, it is on an even longer and more complex 8-year journey, performing a series of gravity assists around both Earth and Venus. Its investigation of Europa will be less intensive than Clipper's, consisting of 2 close flybys, but they will be immensely valuable. Its instruments, including its own ice-penetrating radar, will provide a crucial second set of data points, complementing Clipper's findings and providing a more complete picture of the moon. JUICE will then turn its primary attention to Ganymede, the largest moon in our solar system, and the only one known to generate its own internal magnetic field, a discovery that hints it too may have a subsurface ocean. The ultimate goal of the JUICE mission is a historic first. After its tour of the system, it will fire its engine and become the first spacecraft in history to enter into orbit around a moon other than our own, becoming a permanent artificial satellite of Ganymede. Together, these two great missions represent the most ambitious and comprehensive reconnaissance ever attempted of the outer solar system. They are our robotic proxies, the next great leap in our quest to understand the worlds that share our sun. They are not designed to find life directly, but to characterize the European environment in detail, to assess its habitability on a global scale. They will create the maps, measure the ocean, and taste the plumes, providing the detailed roadmap that will be absolutely essential for the even more ambitious missions that must follow. The landers and the cryobots that will one day seek to touch the surface, and perhaps, eventually, to descend into the profound and silent darkness of that hidden, waiting ocean. The roadmaps created by Europa, Clipper, and JUICE will be invaluable, but they will also be maps of a treacherous and hostile frontier, highlighting the immense practical difficulties that stand between our current capabilities and the ultimate goal of exploring that hidden ocean directly. The challenges are monumental, forming a multi-layered gauntlet of natural hazards and engineering impossibilities that must be overcome one by one. The first and most pervasive of these challenges is, as always, the radiation. While a spacecraft like Clipper can be designed to mitigate this danger with a clever orbit and a heavily shielded vault for its core electronics, a future lander, and particularly a submersible, would not have the luxury of retreat. Any vehicle that seeks to operate on or within Europa for an extended period must be built to endure a constant, withering assault of high-energy particles. This radiation is not just a threat to electronics. It is a force of chemical alteration, one that actively destroys the very organic molecules that a mission would be designed to search for. The surface of Europa is, in effect, being continuously sterilized. This means that any lander searching for signs of life cannot simply scrape the top layer of ice. It must be equipped with a drill capable of penetrating at least several centimeters, or a few inches, into the ice to reach a depth where the pristine, unirradiated material is preserved. This alone is a significant engineering challenge, requiring a robotic drilling and sample handling system that can operate flawlessly in a near-total vacuum at temperatures cold enough to make steel as brittle as glass. But this shallow drilling is merely a prelude to the truly Herculean task, penetrating the main ice shell. The data from Clipper's ice-penetrating radar will be crucial here, for it will tell us just how thick this barrier truly is. If we are lucky, there may be regions, perhaps associated with active chaos terrains or recent plume eruptions, where the ice shell thins to only a few kilometers or a couple of miles. Even this best-case scenario presents an unprecedented challenge. No terrestrial drilling operation has ever been attempted under such conditions, let alone one that must be conducted entirely by a robot receiving commands from 1 billion kilometers, or more than 500 million miles, away. The most promising concept for such a mission is a cryobot, a probe that would not drill mechanically, but would melt its way down. It would be powered by a nuclear heat source, most likely a radioisotope thermoelectric generator, the same kind of long-lived nuclear battery that has powered deep space missions like Voyager and Cassini. This cryobot would be a dense, streamlined projectile, using its intense heat to melt the ice in front of it, allowing it to slowly sink downwards through the shell under its own weight. As it descends, it would spool out a fiber optic cable, its only link to the surface lander, which would in turn relay its data back to Earth. This slender, fragile thread would be its lifeline, transmitting scientific measurements of the ice's composition, temperature, and pressure at different depths, providing a complete geological cross-section of the shell. But the descent would be perilous. The ice is not a uniform, pristine block. It may contain pockets of rock, salt, or gas that could trap or divert the probe. The immense pressure at depth could crush the probe or force the refreezing meltwater into its delicate components. And the slow, churning convection of the ice itself could stretch and snap the vital communications tether. The journey downwards could take years, a slow, blind, and nerve-wracking descent into the unknown. And then, after this monumental journey, comes the ultimate transition. The moment the cryobot breaks through the final layer of ice and enters the alien ocean itself. The engineering challenges here are transformed, but not diminished. The probe, now a submersible, must survive the initial thermal shock and pressure change. It must then navigate in total, absolute darkness, a blackness more profound than that of Earth's deepest trenches, for no sunlight could ever penetrate the thick ice above. It would have to rely on its own lights and active sonar to see, all while being buffeted by unknown currents. The ocean itself, while likely salty, could have a chemistry that is highly corrosive to the materials of the probe. The submersible would need its own propulsion system to explore, perhaps propellers or thrusters, all powered by its onboard nuclear source. It would need a suite of scientific instruments capable of analyzing the water's chemistry in real time, searching for the telltale signs of life. This could include microscopes to look for microbial cells and complex chemical laboratories to detect the specific organic polymers, like DNA or amino acids, that are the unambiguous hallmarks of biology. And it would have to do all of this completely autonomously. The light travel time between Earth and Jupiter is, on average, 45 minutes each way. This 90-minute round trip for communications makes direct, real-time control of a submersible impossible. You cannot joystick a robot when it takes an hour and a half to see the results of your command. The probe would have to be equipped with an advanced artificial intelligence, a mind of its own, capable of making decisions, navigating obstacles, identifying targets of interest, and conducting its scientific investigation without human intervention. It would be less of a remote-controlled vehicle and more of a truly robotic, independent explorer. A scientist in its own right, sent to conduct its fieldwork in the most remote and inaccessible environment we have ever tried to reach. These are not small hurdles to be overcome with incremental improvements in existing technology. They represent fundamental, multi-generational challenges in robotics, materials science, artificial intelligence, and nuclear power. To land on Europa, drill through its ice, and swim in its ocean is a goal that lies at the very edge of what is possible, a dream that will require decades of dedicated effort and technological innovation to realize. It is a challenge on par with the Apollo program's mission to the moon, but one that must be carried out by a machine in a place 1,000 times more distant and 1,000,000 times more hostile. It is the great challenge of a generation, the next logical step in our long, slow, and determined quest to see if we are, in fact, alone in the universe. And so our journey comes full circle, returning us to that faint speck of light that first arrested the gaze of Galileo Galilei more than 4 centuries ago. For all that time, it was a world defined by its distance, a tiny, numbered moon of a mighty planet. But through the patient, persistent gaze of our robotic emissaries, that single point has resolved itself into a complex and captivating world. We have traveled with the audacious pioneers and the revolutionary voyagers that first sketched its impossible face. We have endured the trials of the crippled yet triumphant Galileo spacecraft as it revealed the hidden ocean with the invisible language of magnetism. We have peered through the sharp eye of Hubble to witness the ghostly specter of its watery plumes, a tantalizing invitation to the world below. What was once a simple sphere of bright ice is now understood to be a complete and active geological system, a world of constant motion and renewal, powered by the immense gravitational engine of Jupiter itself. It is a world whose frozen skin is a dynamic map of the forces at work beneath, with great, continent-spanning ridges marking its wounds and chaotic jumbles of ice betraying the moments when the deep ocean has overwhelmed the solid crust. It is a world that has forced us to redefine our concept of a habitable zone, proving that the warmth of a star is not the only source of energy that can sustain a liquid ocean, and that the potential for life may be just as profound in the cold, dark depths of the outer solar system as it is on the sunlit shores of our own Earth. Europa stands today as perhaps the most compelling destination in our search for life beyond our own planet. It is a place where the three great pillars of biology, water, chemistry, and energy, appear to be present in abundance, creating a vast, dark, and ancient laboratory where the experiment of life could have begun a second time. Our story is not over. In many ways, it has just begun. The great explorers Europa Clipper and Juice are already on their long voyage, sent to write the next chapter, to give us the detailed reconnaissance we need to plan for the even bolder steps that must follow. The immense challenges of landing on that surface and descending into that ocean are the great technological quests of our time. But they are quests we will surely undertake. For in the story of Europa, from a mythological princess carried across a great sea to a real world with an ocean of its own, we find a reflection of our own deepest impulses to explore, to understand, and to discover our true place within the vast, silent, and star-dusted cosmos.